the tic-tac-toe problem. And so right now the tic-tac-toe problem is you have the two random drunks playing. Each moment they are as likely to go in any square as any other square. So you have to find a good way to enumerate all possible game states. I was just talking with someone before class that this is in some sense how you build game programs. So in tic-tac-toe, this is a small enough, easy enough game that it's easy to analyze. In fact, you can write a tic-tac-toe program that will always tie or win. What you want to do is you want to write programs that can play at different levels. So for instance, for tic-tac-toe, I was talking about what I'll call the kindergarten program. In a situation like this, X is smart enough to know where to go. Okay? Or if it's like this, we'll assume X is smart enough to know where to go to defend. So you can say, I'm going to have a tic-tac-toe program where if there is a move that I need to do to either win or stop someone from winning, I'm smart enough to see that. But otherwise, I'll just go randomly. A harder thing would be in a situation like this where you go here, they go here. X actually has two winning moves. Where can X go to win, to force a win? Bottom left, or actually over here. X has two winning moves. From direct experience on the elementary school playground, where I am still undefeated, only one tie, most kindergarten kids will not see those as winning moves. Okay? And so when you're trying to write a program, you can easily write a program so that O is playing well here, and O knows to go there. But O will make a mistake and will go there. Chess is a much more complicated program to write. In spirit, it's similar to this. It's just a much harder computation. And so in terms of analyzing, what is a game, chess is a very lengthy computation. I'm not going to risk saying more because this is being recorded. All right, so what we're going to do today is we're going to prove the central limit theorem. We're first going to do a special case for Poisson random variables, then we'll do it in general. I'm going to start off by reviewing a summary of what we essentially are assuming from complex analysis. So briefly, assume we have the moment generating functions of independent random variables exists, say for the absolute value of t less than delta, delta greater than 0. So they exist in some neighborhood about the origin, and we'll assume the moment generating functions are converging to the moment generating function of the standard normal. Then the cumulative distribution function is converging to the cumulative distribution function of the standard normal. Basically, that's the central limit theorem. So the way we're going to prove the central limit theorem is we're going to show we have some type of convergence like this. We have a couple of specific facts we want to use. So the first fact is that if y is ax plus b for some constants, then the moment generating function of y is nicely related to the moment generating function of x. And this was just a simple algebra calculation from the definition of the moment generating function as the expected value. And then the last one, the next one was if x is Poisson with parameter lambda, this is what its moment generating function looks like, the double exponential. It turns out this is a beautiful function to work with for what we're doing. And then the last is, one of the reasons for being why we care so much about moment generating functions. If x1 through xn are independent, identically distributed random variables, so they all have a common density x, the moment generating function of the sum is the product of the moment generating functions. And since they're all the same, I could take just any of them and raise it to the nth power. The central limit theorem can be done in greater generality than sums of independent, identically distributed random variables. It cannot be done in complete generality because if my random variables are dependent, let's say x1 equals x2, let's say x1 equals negative x2. In those cases, I will have very different behavior. In one case, I'm always going to get 0. In another case, I'm basically just multiplying by 2. So when there's dependencies, things can go wrong. They don't have to be identically distributed. It helps. It simplifies a lot of the algebra. And then seeing how far you want to push that, great thing to look at. One last thing worth remarking on is the rate of convergence. As probably you have suspected, I am a Red Sox fan. When I was very young, I asked my great uncle, I was probably maybe 5 years old, will I live long enough to see the Red Sox win? And he said yes. He promised me I would see them win the World Series before I died. I did not ask him how long I would have to wait and what I would have to endure seeing before seeing the Red Sox win the World Series. And as anybody who remembers the 1986 Red Sox, the Bucky Dent from '78, the 2003 He Who Shall Not Be Named as the manager of the Red Sox, there were a lot of things I had to go through before finally I saw the Red Sox win the World Series. What is the connection of that with the central limit theorem? How long do we have to wait before it converges? how fast is the convergence? How good is the approximation? You want to know how good is it. And so there's a beautiful theory called the Berry-Essen theorem, which talks about how quickly the convergence sets in. If you're interested, that's a great thing to read about if you want for your paper, or just something to look at. We're not going to talk too much about rates of convergence, but this is something you need. How many of you have ever been in an elevator? All right, if you're really paranoid, what's one of the first things you look at when you get in an elevator? The weight limit, right? How do you think they calculate the weight limit? You know, if it says 2,000 pounds, do you think it's exactly 2,000 pounds? Hopefully it's a little higher and they're just rounding down to keep people safe. There's some confidence interval, there's some estimates as to where do we think we're going to be safe. In the same thing over here, when we want to approximate something with a normal distribution, we saw sums of uniform random variables, and we saw how very quickly sums of 4, sums of 8 uniform random variables really looked normal. And we saw how bad the exact form, Mathematica basically revolted and refused to do the calculation for sum of 8. It did the sum of 4. We saw that when we were in the art museum, just how bad it looked. You have the exact formula, but it's so unpleasant to use, you just approximate it with the central limit theorem. You approximate it with the normal distribution. What's your error in doing that? A lot of times people say, if n is about 30, that's good enough, as a rule of thumb. For a lot of distributions, at about 30, it's a good approximation. I can come up with a pathological example where n equals 30 is not good enough. But for most of the things you look at, around n equals 30 is fine. All right, so let's do proof of CLT for Poisson. So we will assume x1 through xn are all Poisson with what parameter? We might as well do it, I guess, in general, with parameter lambda, and we will assume independent. What is the mean of a Poisson? Mean is lambda, and so the mean mu equals lambda. The standard deviation, the variance, I guess, lambda squared, right? And so the standard deviation is lambda. And again, we can always see this by doing our calculations, by taking two derivatives, by Taylor expanding. So we're going to let Zn be x1 plus xn. I want to standardize. So if I'm going to standardize, I need to subtract the mean. Well, if each one of these has mean lambda, the mean of a sum is the sum of the means. So I subtract off n lambda. And now I want to normalize it, so I want it to have standard deviation 1. The variance of a sum is the sum of the variances. I don't have to worry about this n lambda, because if I shift everything by n lambda, I'm not changing the fluctuations. So the variance of a sum is the sum of the variances. Each one has variance lambda. Has variance lambda squared. So the variance of the sum is n lambda squared. I divide by the standard deviation. It's going to be lambda square root of n. So this is a quantity that now has mean 0, variance 1. So the expected value of Zn equals 0. The variance of Zn equals 1. And variance just has fewer letters to abbreviate than standard deviation, which is why I write that. Also, it's 1. It doesn't really matter if I'm talking about the variance or the standard deviation. 1 squared is 1. So this is a natural thing to study. This is the standardized random variable. So standardized random variable. Right. What we're going to do now is we are going to do a bunch of algebra. I have deliberately not prepared for today's lecture for two reasons. One is I want to be kind of fresh when I'm looking at the algebra as to how might we look at it. And two, boy, that school committee meeting went late last night. All right. How should we start the proof? All the proofs start the same way. What's step 1? Definition. So the moment generating function of Zn of t is equal to the moment generating function of Z1 plus Zn minus n lambda divided by lambda square root of n of t. Before I start using my facts about sums, and the moment generating function of a sum is the product of the moment generating functions, what I'm going to do is I'm going to use one of my properties, property 1. And actually, what I think I'm going to do is I'm going to replace lambda here with mu and lambda here with sigma. We know that mu and sigma happen to be equal to lambda. But let's keep the calculation as general as possible for as long as possible, so that this will still hold if we weren't looking at Poisson, if we were looking at other random variables. Eventually, we will shift to Poisson because it's going to make things easier. Why is it going to be easier? We have a closed form expression for its moment generating function, which happens to be a nice expression. But this argument is going to be the same again and again and again, so let's just do things in general. Well, if we look at the first statement, if we have ax plus b, then the moment generating function of y is simply related to the moment generating function of x. So here, if we want y to be, a z1 plus zn plus b, we would be taking a is 1 over sigma square root of n, and b would be n mu over sigma square root of n. Please be watching the algebra. The probability that I make an algebra mistake is almost 100%. Yes, I made it that far.
No, it's not.
Oh, good.
I was just saying, so when you switch the...
Oh, good. This should be a minus sign. Yes.
No, that's not.
Damn it. Hide.
I was just asking, so when you switch the mu and the signals for lambda?
Right.
Right, because you know that for Poisson.
Well, for Poisson, we know the standard deviation is lambda, and we know the mean is lambda. I want to consider a more general, and these should be. Sorry.
Why did you change it if you wanted to keep it as general? Doesn't that only hold for...
I'm sorry?
Doesn't the change that you did only hold for...
Over here?
No, but when you...
No, because I'm just saying, this whatever the mean of the x's is, that's mu. Whatever the standard deviation of the x's is, that's sigma.
Okay, yeah.
Right.
In this case, it's just called that.
Right. And then we actually know that their values happen to be lambda and lambda. But this way, I can set up the calculation and just do the calculation once. And then at the end of the day, we're going to run into some algebra. And we can simplify things by saying, hey, in this case, lambda equals sigma equals mu. And then we'll be able to simplify the calculation. OK, but I did make a minus sign mistake, so it was good to stop. All right. So now we get the moment generating function of Zn of t is going to be e to the bt. So it's going to be e to the negative n mu over sigma square root of n. And now we get the moment generating function of x1 plus xn evaluated at a times t. And a is 1 over sigma root n. So t over sigma square root of n. Bless you. What happens as n gets very, very large? Where am I evaluating the moment generating function? Basically at 0. OK? What's the value of the moment generating function at 0? So if you take the moment generating function and you evaluate it at 0, what do you get? So the moment generating function of any random variable, it's the expected value of e to the tx. It's the integral minus infinity to infinity of e to the tx fx of x dx. It's the sum of mu n prime t to the n over n factorial. N goes from 0 to infinity. If I evaluate the moment generating function at 0, what do I get? What's the first term in the expansion? Or if t equals 0, what do I get over here? I just get 1. So we get the moment generating function at 0 is just 1. Well, we're not evaluating it exactly at 0. We're evaluating it very close to 0. So what we're going to want to do is we're going to want to do a Taylor series expansion of this. What's nice is because we have a square root of n, yes?
Could there be a t in the exponent, or why is it not t?
In which exponent?
E.
Here?
Up 1.
Here?
Up 1.
Oh, here? I probably dropped the t, thank you. Thank you. Yes, that would be very bad later. See, I told you there'll be high probability of mistakes. All right. So we're going to be evaluating this very close to the origin. So when we do the Taylor series expansion, as you take higher and higher powers, t is fixed and is going to infinity. Well, then the next term will be a t squared over sigma n, a t cubed over sigma cubed n to the 3/2. As we go deeper and deeper and deeper, we're dividing by more and more and more, and these terms are going to become negligible. So when we do the Taylor series expansion, we're not expecting many terms to survive and contribute. There is, however, a reason why we don't expect this to just be 1. We have n terms here. We're taking more and more pieces. So because we're taking more and more pieces, even though we're evaluating it very close to 0, we have infinities going in 2 different directions. We're dividing by infinity, but we're taking infinitely many terms. And whenever you have 2 infinities interacting, it's always a tug of war. It's always a difficult situation to see which wins. All right, so what's going to go on here? Well, we expect it to be close to 1. Now we use the second property. This is just e. All right, the n cancels a little bit. It'll be negative mu t over sigma square root of n. I cancel the n. And it'll be the moment generating function evaluated at t over sigma square root of n. And we raise it to the nth power. So it is worth saving this formula. Yes?
Would square root of n be on top for the e?
Yes. So that's right, square root of n mu t over sigma. Thank you. All right, this is the formula worth saving. What do you want to do at this point? What's your instinct at this point?
Logs.
Take logs. We have a product going on here. We have something to the nth power. Normally you would take logarithms of both sides. And if you take logarithms, oh, I've got an e to a something. Boy, that is set up nicely for a logarithm. I've got this raised to the nth power. That's set up nicely for a logarithm. I am not going to take logarithms right now because the Poisson is so nice. But in general, you would take logarithms. Now let's use Poisson. So for Poisson, so now it becomes special. M zn of t, well, in the Poisson case, mu equals sigma equals lambda. So now we get e to the negative square root of nt. And now the Poisson, it's going to be e to the lambda. And now we get e to the t, but t is t divided by lambda square root of n minus 1. And the reason is we're evaluating the moment generating function of the Poisson not at t, but at t divided by sigma square root of n, and sigma equals lambda. So sigma equals mu equals lambda for the Poisson. Okay, so now we want to analyze this. If we're trying to show it converges to the moment generating function of the normal, the standard normal, we should be getting e to the t squared. All right, I've got an e to the t here, which I don't necessarily like. But we're going to be having some stuff over here. So let's look at e to the t divided by divided by lambda root n minus 1. This is going to be t. Okay, I'll write it slowly. It's 1 plus t over lambda root n plus 1 over 2 factorial t squared over lambda squared n plus 1 over 3 factorial t cubed over lambda cubed n to the 3/2 plus dot 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 minus 1. So I'm just expanding the exponential. The 1's cancel, and I get a t over lambda square root of n. Oh, we made a mistake. Going from this line to this line, what did I drop? I dropped the n. right? We're raising it to the nth power. There should be an n here. All right, so when I look at e to the t divided by lambda root n minus 1, I get t over lambda root n plus 1/2 t squared over lambda squared n plus 1 over 3 factorial t cubed over lambda cubed n to the 3/2 plus dot dot dot. And this is e to the t over lambda root n minus 1. All of this is in the notes in the book. I'm doing exactly the same calculation. If you just want to watch this, just watch it. But this is not the quantity we need to look at. We need to multiply it by n times lambda. So let's look at n times lambda times e to the t over lambda root n minus 1. So if you notice, what I'm doing is I'm slowly doing the algebra. I'm not worrying about this e. Why am I not worrying about the e? At the end of the day, I'm trying to get e to the t squared over 2. I've already got e. I just need to look at the exponent. All right, now we multiply by n lambda. All right, so the n hits the square root of n over here, and we're left with the lambdas cancel, which is not looking good. Oh, no, that's good. OK, good. The lambdas cancel. We have a square root of nt. The next term is a 1/2. One of the lambdas cancel, so I have a lambda down below. The n's cancel, and I have a t squared. Little worried. The next term will be a 1 over 3 factorial t cubed. Wait a minute. Okay. Okay, so now we'll have a lambda squared n to the 1/2 plus dot 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 dot. All right, so there's a small algebra mistake that I'm a little bit worried about right now. So this should not be a lambda here. That lambda should be gone at this point. And so let's see. The standard deviation is just lambda. So we should have all right, is anybody seeing an algebra mistake? This is going to be really valuable if somebody can find the algebra mistake right now. Are we positive that we've got the right mean and the right variance for the Poisson? Is the variance lambda squared or lambda?
Maybe the variance is lambda, the standard deviation is squared.
Maybe. So so how can we check and see if we've made a mistake?
Check the textbook.
We could check the textbook. What else could we do? What can we do if we think we made a mistake?
Units.
We could check units. And so if we look at a Poisson process, lambda is, I think, a number of events, right? So lambda is not going to have units. So unfortunately, while that's a great thing to do, we're not going to detect it. What can we do to figure out if it's lambda or lambda squared for the variance? What can we do? Derive it again, right? mx of t is equal to e to the lambda e to the t minus 1, which is e to the lambda. And now when we do e to the t minus 1, we get t plus t squared over 2 factorial plus t cubed over 3 factorial. I'm sorry? So I think the variance might be lambda and we might be getting a square root. So I think we've just written the wrong thing. So this is actually not bad to make a mistake like this, to then figure out how can I quickly check. Well, now we expand this and we get 1 plus lambda t plus t squared over 2 factorial plus dot 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 plus lambda squared t squared plus, I'm sorry, t plus t squared over 2 factorial plus dot 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 squared. All right, so we have 1 plus lambda t. Now we're going to have a lambda t squared over 2. And when we have this, we'll have a 2 factorial here from expanding it. So we have a lambda plus lambda squared t squared over 2 factorial. So the expected value of x squared for Poisson is lambda plus lambda squared. So when we subtract the mean and we calculate the variance, so we get the variance of x is going to be lambda plus lambda squared minus the square of lambda, which is equal to lambda. All right, so sadly, nobody caught me when I made the mistake. So we have to come all the way back to here. And for Poisson, it's not lambda. It's a square root of lambda that has to go in there. So when we come over here, and again, not much changes. Everything is fine over here. And now you can see the advantage of doing a calculation in general, because all of these steps are perfectly fine. All right, so again, did not deliberately make this mistake, but since I made it, let's take advantage of it. So we get sigma equals square root of lambda, and we get mu equals lambda. So now instead of getting negative square root of nt, if this is lambda and this is square root of lambda, it should be, I think, negative square root of n square root of lambda times t. And now over here, sigma is equal to square root of lambda. So it should be t divided by square root of lambda n. Okay? So now we come over here, and now we have to replace lambda with the square root of lambda. So fortunately, not much changes. This becomes a 3/2. This is a square root of lambda, square root of lambda, lambda, lambda to the 3/2, square root of lambda. Now we still have a lambda over here. So a lambda times the square root of lambda, this is going to get us a square root of n square root of lambda t. Now the lambda times the 1 over lambda, the lambda is gone. And then down here, we'll have a square root of lambda. Okay. So we can now get rid of all of our algebra calculations. But again, this is why it's very useful to know these formulas. If you make a mistake, and mistakes happen, you can correct. And so now we get that the moment generating function is going to be e to the negative square root of n square root of lambda t. And now from this piece, it's going to be e to the square root of n square root of lambda t plus 1/2 t squared plus 1 over 3 factorial t cubed over lambda to the 1/2 n to the 1/2 plus dot dot dot. Well, we have an e to the negative square root of n square root of lambda t, e to the square root of n square root of lambda t. Those two terms completely cancel. We have an e to the 1/2 t squared. So we get the moment generating function of zn of t is e to the t squared over 2. And now we have e to the 1 over 3 factorial t cubed over lambda to the 1/2 n to the 1/2 plus dot 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 dot. As n goes to infinity, what happens to all these terms? What happens to all these terms in the exponent as n gets large? It approaches 0. What's e to the 0? 1. So what we get is that as n goes to infinity, this converges to e to the t squared over 2, and that finishes the proof. So this is the proof of the central limit theorem for the case of sums of Poisson. All right, let's go through what we did. The main thing was we start off by saying, we've got our formula for the generating function of the sum. We've standardized our random variables. We get this nice expression. We then substitute, eventually correctly, for the values of lambda for mu and square root of lambda for sigma, and the fact that we know the moment generating function. Because we know the moment generating function, we can work with it directly. We do a little bit of algebra. And then we get that the moment generating function is equal to the moment generating function of the Gaussian times something that's rapidly going to 1. and there's the convergence, and then we go all the way back and we appeal to our results from complex analysis. And from our results from complex analysis, we now know that the cumulative distributions functions converge, so the densities converge. That's the central limit theorem. Okay? All we have to do now is basically say, instead of using the Poisson, let's just do something in general. All right? If you want, you can listen and know that on your final midterm, there will be a question that asks you to do something like this for a specific distribution. I don't want you to go through the argument in general, but on the final, I'll give you some random variable and ask you to just mimic this calculation. It's a good calculation to know how to do. Usually it's easier than the general argument. What we want to do now is we want to say, well, what if we didn't have a Poisson? What if we had something in general? How would things change? What made this not so bad is we had a nice form. All right, well, if we don't have a nice form, we can still expand. The key thing was that the higher order terms did not really matter. And after we do the proof, we'll talk about the consequences of why this doesn't matter. All right, so again, this can now be killed because we don't need this. And so now this will be the general case. So now, if we're doing the general case, now we'll do logarithms. Absolutely. The log of the moment generating function of t is going to be square root of n mu t over sigma plus n times the log of the moment generating function at t over sigma square root of n. Okay? Now, approximately, when n is really, really large, what is the moment generating function being evaluated at? We're evaluating it at 0. The moment generating function at 0 is 1. The log of 1 is 0. So we expect this term to be going to 0, but we're multiplying by n, which is huge. So because we're multiplying by n, there's a chance for this not to go to 0. It better not, because we've got a huge thing here going off to minus infinity. So we have to do a more delicate analysis of how does this balance with that. We're going to Taylor expand this. So we have the moment generating function of x at t is 1 plus mu t plus mu2 prime t squared over 2 factorial plus mu3 prime t cubed over 3 factorial plus dot dot dot. Well, where do we want to evaluate the moment generating function? We want to evaluate it at t over sigma square roots of n. So it's 1 plus mu t over sigma square root of n plus 1/2 mu2 t squared over sigma squared n plus 1 over 3 factorial mu3 prime t cubed over sigma cubed n to the 3/2 plus dot dot dot. Okay? So this should be the moment generating function of x. When t is very small, these higher terms don't matter. Now there's a miracle with the central limit theorem. It's not, if you take a sum of normals, you get normal in the limit. Or you take a sum of uniforms. It's basically take anything nice and look at the average, and that average becomes normally distributed. This is remarkable universality. It's basically saying, I don't care what distribution you look at. Essentially, all you need is a finite mean, a finite variance, and basically a finite, say, third or fourth moment, and that's going to be enough to make things work. We're assuming a little bit more. We're assuming the moment generating function exists. For the moment generating function to exist, all the moments must exist and be finite, and this series must converge in some neighborhood. So the Cauchy random variable would not work. But a modification of the Cauchy, some constant 1 over 1 plus x to the 2004, sums of this become normally distributed. We would not be able to prove this because it doesn't have all its moments finite. Its moment generating function does not exist in a neighborhood. So proving that is beyond our techniques, even assuming the results from complex. Why do we have this incredible universality? So when you see the central limit theorem, you should be shocked at how little you need to assume. The reason it doesn't really matter is where does the shape of the distribution come into play? If I give you any distribution, I can always rescale so that it has mean 0. Right? Just subtract the mean. I can always rescale so that it has variance 1. This is why we have the Celsius scale. It's a simple linear rescaling of Fahrenheit. This is not deep. Okay? What this basically tells you is if I give you a probability distribution and I tell you the mean and the variance, I've really given you very little information. Because I can do a linear transformation and relate any two distributions so long as they have finite means and variances. So if I tell you, the mean on the class was 104 and the variance was 2, if it's on a normal absolute scale, that's pretty good. If I'm using some kind of strange funky grading, not necessarily. You need to know what kind of system I'm using. So what it's basically telling us is no matter what distribution I give you, I can always standardize it to have mean 0, variance 1. The shape of the distribution is not met until you reach which moment? Which is the first moment that really gives you information about the shape of the distribution? The third. And if your distribution is symmetric about the mean, it'll be the fourth moment that gives you the shape. So if I want to see anything about the shape, I don't start seeing the shape until here. So this is where the shape enters. This is all universal after standardization. And so if you look at the Taylor series expansion, the shape is only coming in over through here. You have this universal part in the beginning, which you can normalize, and the shape of the distribution won't matter. Why is this useful? If I now look at the log of the moment generating function at t over sigma root n, I'm going to use the log of 1 plus u is equal to u minus u squared over 2 plus u cubed over 3 minus dot dot dot. And this whole expression here is u. For those of you who are still writing, you're welcome to do that. But again, I strongly urge you just sit back and try to enjoy the algebra. I wish I could just sit back and enjoy the algebra right now. I debated doing this by PowerPoint. All right, this whole thing, sorry, I should not say that by Beamer. I would never use PowerPoint in public. All of this stuff over here, that's going to be my u. Now, I'm going to be multiplying by n. So over here, this term, when I multiply by n, is that going to be large? Yes. N divided by square root of n, that's going to be large. N divided by n, that's going to be large. That's going to be of size 1. N divided by n to the 3/2. I don't need to worry about this. So when I multiply by n, I'm not going to need to worry about the t cubed or higher terms. Because even when I multiply by n, they're going to be negligible in the limit. So in terms of what I'm going to write down, I will have mu t over sigma square root of n plus 1/2 mu 2, I guess that should be a prime, t squared over sigma squared n plus dot dot dot. That's my u term. Now I subtract off 1/2 of u squared. So mu t over sigma square root of n. Do I have to worry about putting in this next term for u squared? I'll put it in for now as you're thinking. Well, if I look at this, I'm squaring it. The smallest this can be is if this hits the t over square root of n term, which is going to give me, this was sigma n. And then over here. So the smallest this is going to give me is an n to the 3/2. Even when I multiply by n, it's still going to be negligible. So I can write this as the log of mx t over sigma square roots of n times n is going to be, so I multiply through by n. When the n hits this, I'm going to get n mu square root of n mu t over sigma. Beautiful. That's going to perfectly cancel with that. I don't even have to worry about what everything is. The next one, I'm going to have 1/2 mu 2, the n cancels the n, sigma squared. And now over here, what am I going to get? When I square this, I'm going to get a minus mu squared over sigma squared times t squared plus dot dot dot. Does anybody remember what mu 2 minus mu squared is? That's the variance. This is the second moment. I'm subtracting the square of the mean. That's the variance. The variance divided by sigma squared is 1. So when we substitute, we get the log of m zn of t. So the key fact is we note mu2 minus mu squared is sigma squared. We get that this is equal to, this cancels with this. We have 1/2 t squared plus something divided by square root of n plus more over n plus even more over n to the 3/2, blah, 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 blah. If you want, what you have to do is you have to now just rigorously show that this series converges and is going to be something nice divided by square root of n. What class do we do this in? I'm sorry? Real analysis or Calc 3. You're supposed to have seen some basics of sequences and series. We have the moment generating functions exist. These series will converge. These will be less than 1 as we take higher powers. I'm not going to go through all the algebra of the convergence of the sequence and series. I hope it's reached the point where you can see it's very reasonable that these things will converge. It's a good exercise to dot the i's, but this is all going to go to 0 as n goes to infinity. So as n goes to infinity, the log of m zn of t goes to 1/2 t squared, which implies m zn of t goes to e to the t squared over 2. And that's what we wanted to prove. The proof, I think, is a little bit easier in the Poisson case than in this case. You've got to expand the logarithm. You've got to work a little bit more generally. You've got to remember this formula. You've got to take squares. You've got to do the algebra. But it's essentially the same proof. What I like about this proof is it shows you why the central limit theorem is true. Is that the shape of the distribution does not kick in until here. And as we do the analysis, that comes in as a lower order term that's going to vanish in the limit. The shape of the distribution should matter. So how does the shape of the distribution affect the central limit theorem? It affects the rate of convergence. What do you think would help have a good rate of convergence? I'm sorry? Symmetry. So maybe if mu3 prime is 0, that might help us. Which kind of makes sense. If it's symmetric, you may be as likely to go above as below, and you'll have a lot of these things canceling each other. So maybe mu3 prime being 0 will help us. A smaller value of mu4 might help us, because then the next term will be even smaller. Okay. Any questions about the proof? So this is a long, big algebra proof. All right, but this is the central limit theorem. This is a major accomplishment. Now, of course, I was just at the Hall of Fame. I saw the Barry Bonds asterisk ball. There should be an asterisk by our proof, so I will put a little asterisk over here. I know it's not because of what I was on last night as I was preparing the lecture. Why is there an asterisk? Why is this not a proof? I'll stand in a strategic place. Why is this not a proof? Yeah, because we're assuming some really heavy machinery from complex analysis. So what I thought I would do is, we've got a little bit more than 2 weeks left. And so one of the things I thought I would do is show you a little bit of complex analysis to get a sense of why these things are true, why things break down. Complex analysis is one of the most beautiful subjects in mathematics. It takes hard integration and converts it to easy. You are supposed to be thinking about the convolution of Cauchy with Cauchy. We'll probably talk about that on Monday. Complex analysis allows you to bypass that integration and convert it to an algebra problem. I can do basic, well, okay, I can't, but most people can do basic algebra. In most situations, this is an advantage. So let me just talk a little bit about why this works. So the moment generating function of x, it's the expected value of e to the tx. It's the integral from minus infinity to infinity of e to the tx fx of x dx. And similarly, if I give you the moment generating function of y, you're integrating e to the t, I can use the same letter, x fy of x dx. Two different densities. If the two densities are equal, what would you like to conclude? I'm sorry, if the two moment generating functions are equal, what would you like to conclude? The densities are equal. Unfortunately, I can have two integrals that are the same that don't necessarily have the same integrand. The advantage we have is we have, say, mx of t equals my of t for all t less than delta, delta greater than 0. So what this is telling us is there's infinitely many choices of t, an entire interval where these are equal. So the hope is that if you have things that are equal many, many, many times over, the only way that can happen is if the integrands are equal. So imagine the following. We have, given some functions f of x, g of x are continuous for any piecewise continuous h, we have the integral from minus infinity to infinity of h of x, f of x dx equals the integral from minus infinity to infinity of h of x, g of x dx. So whenever you take a piecewise continuous h, these two integrals are the same. What would you like to deduce? So what should be true? F of x should equal g of x. Any thoughts as to how we might show that f of x equals g of x? So we claim f of x equals g of x. Any thoughts as to how we might show that they're the same? So this is a great time for proof by contradiction. If they're not the same, they must be different at some point. So assume there exists an x naught such that f of x does not equal g of x naught. Without loss of generality, let's assume f of x naught equals 1, g of x naught equals minus 1. Is there any real loss in assuming this? No. I can always rescale. I can add a multiple to each function. I can add a constant to each function. I can assume something like this. So here's what's going on. I have x naught. F of x is over here. G of x is over here. Because my function f is continuous, f has to be positive in some small neighborhood about x naught. Similarly, because g is continuous, g must be negative in some small neighborhood of x naught. What I can now do is, this is true for any piecewise continuous function h. Let's choose h to be 0, and then 1 in a very small interval, and then 0 again. And you will do the same thing over here. And so we have h is 1 near x naught, 0 otherwise. So then the integral of h of x, f of x dx is going to be approximately equal to something positive, right, times whatever that width is. And similarly, the integral of h of x, g of x dx would be something negative. Contradiction. So we get f equals g. So it's very important that f and g be continuous here. But the idea is, because they were continuous, because we had the sequence of test functions we could look at, we could then improve and go that f had equal g. This is briefly what's going on with the proof of the central limit theorem. This is briefly what's going on with this e to the t. And so we'll talk a little bit more about why that's going on.